Okay, thank you. This is, thank you for that introduction. And so you basically know what my talk is about now. And I first want to give you a small introduction on where I'm from. I'm basically here from the forest. There's a research center. It's like slightly outside of Dresden, and as I do, large research centers are usually like in the forest outside of the cities. And we have some major facilities like large radiation sources, high magnetic field laboratory, and ion beam centers where they work with ion beam material modification, and of course high power accelerators, which are in the focus of this talk. My background is that I'm active member of computation science group. We basically do some kind of a good old consulting for all the other institutes in the center. For example, we do this thing working with the laser here. And then my actual background is in statistical physics and theoretical solid state physics. We'll first start by giving you some more details about the motivation for this work. So that is the parallel high power lasers phase, was already mentioned in the introduction. Then I will introduce our deep learning problem. I will give few basic details about what the deep learning is, in case someone didn't, and someone needs it now. And then also the definition of our problem, so that's well defined. Then I will give you the main part, the overview of what we are actually doing, how we solve this problem, and what the problems are. And the actual main problem what we have is lack of data, severe lack of data. And then the main result we have, basically interesting results, like it's about the generalization ability of GoogleNet, which I can show in some cases. In some cases, because we don't have enough data, it doesn't really work. And then I will give you an outlook on where we plan to go from there once we have enough data to try different things. So regarding the high power lasers, we have one which is currently running called Draco. It's a 150 terawatt laser. These lasers are pulsed. They fire femtosecond long laser pulses. So this one 150 terawatts, this one 1 petawatt, which is currently under construction. And these fire at 10 hertz. That's basically what is delivered for the experiment at the end. The experiment at the end is things like where they investigate the states of matter in high electric and magnetic fields, which is what the laser basically is, strong oscillating electric and magnetic fields. And other things are particle acceleration. For example, if you have like matter is like made of electrons and positively charged cores, or charged particles basically. And if you fire in there with a high electric field, then you basically move these charges around and you can accelerate them also. So you get like a really small particle accelerator if you discount for the huge laser at the other end. Just to give you some coordinates where this talk is basically taking place. This laser is have this amplification phase where the laser is running through lots of elements, like also it is pumped in nonlinear crystals. Then it's focused, and then it comes to the experiment where you actually have this energy density which you need for the experiment. We are here in the amplification stage where the laser beam is not focused. So the energy density here is much lower than at this point. Here, if we would have this energy density here, then things would break immediately. And this is basically what the talk is about. It's already intense light, so basically components, they are basically running at the limit already. Components age due to the stress, and at some point they may break. And if you have a damaged mirror in our system, then it diffracts light differently and may add some other focal spots which can have different components. And then one broken mirror will basically hit another component, which will also break. This one will break another one. You get a cascade, and if you don't stop it, it will break your whole laser. And this one gets really expensive if it hits a crystal, which take like months to grow. They are grown on demand, and they cost hundreds of thousands of euros. So it's expensive and gives you a few months downtime if this happens. There's currently a beam monitoring system in place, which basically takes part of the beam through a semi-transparent mirror, recorded by a camera, and you get these laser cross-sections. This is what we are working on. And sometimes when you have a broken mirror in the beam, you see something like this. I hope you can see this. Also on the screen, there are these small features here, which look like concentric rings, which are not completely circular in shape. So there are these caused by these diffraction centers you have in this formed on the mirror surface. And these are basically the things that focus light in uncontrolled ways. So basically, you can see these patterns here. The human operator, can also identify these patterns and see them in the beam. So when they set up the laser, they actually configure this and make sure that it's clean. And so that everything is working. But then when you start to fire at 10 hertz, they can't really, check between two beams. Between two shots. So that's basically what the automation is about, getting the thing faster. Not something a human couldn't do, but something a human can do very well, but not this fast. And that's what I already said. This is basically a proof of concept for detecting the signs of a broken mirror. There are other signs of things which may be wrong in a laser, like there could be dust inside, there could be other misconfigurations. But this is what we have test data for, or at least a little test data, which we can use. So our deep learning problem, let's start first with introducing deep learning. That's a nice comic about deep learning. It's often seen, like you put data in, you have a pile of linear algebra, you stir it a bit, and then you get your answers out. To make this a well-defined problem, you need to first settle some points. First thing is, what do you want to classify? That's basically what is the problem in this case. So that's the first thing we will also talk about. And then what kind of data are you looking at? This also, again, defines what you can classify, because your data controls what you can learn from it, actually. So important is the data must be representative of the problem. And basically, our proof of concept is working in a way, but we have a problem with low data. So basically, we have an example here also of how our data is not really representative of everything. And ideally, you want to split your data set into training, validation, and testing. The reason why it's 3 sets is actually because you often use your validation set for hyperparameter optimization, and so it actually influences your result. You're not training with your validation set, but you are kind of training your hyperparameters with the validation set. That's why you have a third testing set, which you never touch during your whole training routine. Then you have your network, in case you do deep learning. In this case, we are doing deep learning because we're working with images. Deep learning has been proven to work well with images. So there's the size of your network, how do you train it, and then it needs to be able to generalize. You don't want to have overfitting. And basically, you do this in a cycle, everything. And one part of the cycle is this nice analogy by Andrew Ng from Google, now Baidu, who made this analogy about rocket engines. You can build, using GPUs and such, you can build lots of large rocket engines, which are your networks, basically. But in large network, you need to feed with lots of fuel at the data, basically. If you have a larger rocket engine, you want to have more data. If you have more data, you can build a larger rocket engine. Maybe you even want to. About the data. So that's saw this before. That's a good image. At least that's one where the laser, where no mirror is broken, and that's where the mirror is broken. So that's what kind of type of data we have. The problem here is this is another picture of a broken mirror. That's basically all the data we have in a way. The problem is these are different pictures, so there's some noise basically differentiating these two things. But we only have one series which the people who operate the laser gave us to work with, because somehow they can't break too many lasers and give us lots of pictures of this. And then there's another problem, because the system is not always really clean, especially in the configuration, especially the optics giving us the pictures, these pictures. So this is another picture of a data set we got later, actually. And what you can see here is there's a feature inside which looks rather similar to these concentric rings, which are not completely circular in shape. But they told us that's not a problem in this picture, because this was a new example for a good picture. Actually, from a data set I will talk about in the end regarding the outlook. So we can't do whole image classification on this for these two reasons, basically. We don't have enough picked images to train. If we would train on this image, we would learn this image is bad, but only with the 3 dots there. We don't learn anything else. The other thing is, if we classify this image as bad then, because we learned that these features are bad, then how do we tell the network, to tell the program basically this image isn't bad in this case, but we still want to use the system afterwards to look out for new features occurring. So that would be something nice for unsupervised learning, but then there's a problem which is this thing here. I haven't yet seen a really clean picture to actually detect anomalies, to actually train for anomaly detection, because there's no picture without anomalies. So at this point, we could basically retitle the talk to like training images with like 2 images. So fortunately, let's just first go on to the network we are using. At the time, we didn't have much experience in designing a network ourselves, basically. There are lots of things, especially the overfitting problem and such, which you need to take care of. And Google designed this GoogleNet for the ImageNet challenge, and it proved to work really well, and it's also not overtraining, even on rare samples. There are some measures in it, like dropout layers, which were used at the time. And yeah, so that's just what we are using there. There are some obvious counterindications why we wouldn't use this. We will basically want to classify things into 3 classes, not 1,000 classes. And the patterns we have are not really complex. We want to classify these rings. We don't want to discriminate different breeds of dogs. So we could also work with a smaller network on this, basically, which would also save on computation time. But for now, we work with this, which is also works. So our approach. First, I want to tell you some approaches we don't use, which would be really nice to use, actually, but mostly we can't use them because of too little data. One thing is this image segmentation problem, which you heard there were a few talks before about image segmentation. But for this, you basically need to have training on whole images, so that you then can basically turn the network around and tell you, okay, what was the feature that told you that the image was bad to do the segmentation. Something else that would be more feasible, doing object localization using a sliding window. But then remember, we have like 100 milliseconds to classify this. So we can't really do like lots of small classifications on this. We need to reduce the amount of this. Then there are approaches where you don't do the sliding window approach, but you train a network to suggest regions. But that's a problem. To train a network to suggest regions, you also need to do a whole image classification in the first place. But the region suggestion, or the candidate region thing, is basically what we are going for, but we are just doing this classically. We're doing classical feature detection in our image. And what I mean by classical, we just use like image processing tools that have been used for a long time, like in this case a bandpass filter. So when we have our beam here, that's basically a rather homogeneous thing. The ideal beam is really homogeneous or maybe Gaussian or something, but it has a simple structure. So basically the whole structure of the beam can be subtracted. That's basically long wavelength. Then we have some noise, which you're also not really interested in, so that's short wavelength. So we have a bandpass filter, and everything that basically sticks out here is probably a feature. It's probably something which may be wrong. So then this is basically a really cheap threshold approach. Just in this case, for example, it's a 4 sigma threshold we set here, and we basically catch these fluctuations in there. But that's not really reliable. You can get random fluctuations which are this way. In some pictures, you don't want to have 5 sigma, but you want to have it lower, but this also gives you more false positives, and that's where the machine learning comes in then. Let's first talk about the image, the candidate regions. The thing is, we don't want the network to since we don't have a lot of data, the network it's hard to train the network for everything. So we're basically trying to put as much knowledge as we have about the system, or the physics of the system in this case, into our program before we apply the machine learning algorithm. Because this way, the machine learning has it easier to do things. It doesn't need to learn things we already know. Especially, for example, we start out with this with the threshold, and then we basically only mark features as such, which basically have one thing which goes below the threshold and one thing that goes up, goes 1 pixel below, 1 pixel up, or 1 pixel region below, 1 up, or 2 below, 2 up, something like this. Because we have these concentric rings, we will always have a pattern like this, which is the interesting thing here. And this basically looks like this. So what we get there, already looks like some labeling, but that's actually just the feature detection. That's no learning there. And what we do from this, where we take these labeled pixel regions, we group them, calculate some bounding boxes, tight bounding boxes around those, and then we basically map them to, or cut out 64 by 64 pixel regions. That's basically just the image size we classify. So Also, it's small images, so we can classify them quickly. Doesn't take too many input neurons there. And yeah, basically, if they're too large, we just scale them down. If they are smaller, we just cut out a larger region around it, so we don't need to, and we keep it square, so we don't add any things which make it problematic, like some tilt or some scalings. So the classes we are classifying into are then the true positives. That are the things we actually want to see as being, which are pointing to the broken mirror. Then sometimes we have these random occurrences of something which peaks outside of the margins, and that's not so bad. We don't want this. So that's a false positive. So we want to classify this as false positive. So basically, in the end, we could have like false positives, true positives in this case. And we have these edges. That's basically just for future extension. Basically, we detect edges, because edges could also point to not only the edge of the beam or bad aperture in the imaging process, but objects which have been put into the beam, and which we might also want to localize. So these are the three categories we have. And we have an intuitive understanding on what these look like. And basically, we want to transfer this intuitive understanding, which we use for labeling these images, to the computer, which is basically what data-driven deep learning is. And so this deep learning is really was developed for like crafting classifiers. Basically, you could handcraft them, or you could use the neural network to craft these classifiers for you based on data, or developing heuristics to recognize something or to decide something based on data. Okay, so then the idea here is where we have these features. Basically, we just register. We just want to register what patterns are there, especially what are these bad patterns. We want to report them to the operator, put the laser basically in a safe operation state, so it suppress the next shots basically, so it doesn't break itself, while the operator decides what to actually do with these, because one of the features, a similar feature might occur and it's not so bad. So basically, then the operator would basically mark the region as, okay, there's a feature now in our beam, but I won't remove it. It's not bad. So basically, that's when it's in your optics, basically, which the operator can then determine by doing some manipulations to the beam. You don't want to do this automatically, because then you might influence what the outcome is of the experiment at the end. You can't do that. We can just passively look at it. And yeah, on the other hand, the human might decide that's actually a bad feature, so I need to shut down the laser, go and clean it, or replace the mirror. Okay, so that's the setup of our problem, basically. And the implementation here in production for this, the target for production is we use C++, especially because we need this low response time. So Python is good for prototyping and testing things, but if you have like logic in Python, it takes a long time to run, basically. If you want throughput, you can do it in Python, because you just call a C function on lots of data and then it's running fast. But if you want to have short reaction times, you are doing logic and you call a small C function or something. So we need to stay in this 100 millisecond regime there. We use Caffe for learning because it has a good C++ interface, good C++ API. The TensorFlow API, C++ API, for example, is not so well documented. I think it's not at all documented so much. Python API is well documented. And yeah, and it also provides a program for multi-GPU training. So actually, for training, we don't use specific code. We basically put in the network in this proto-TXT format, which is the Google Net. So we don't craft this ourselves in this case, or didn't do this at this point. And we can just train it on multi-GPU, which works really well. We just need to, before compute our data, prepare our data. And this is what we are doing then with OpenCV. So for the image part of the image processing, we use OpenCV, which has a good interface to Caffe. So I hope that's something you can use. And from our data, so basically from this one experiment set of data images that we have, we can extract like 389 candidate regions, which are like all these false positives, edges, and the true positives. And we reserve 89 for validation. Especially what we reserve for validation is this region here. So we also explicitly reserve one of the features for validation, which will lead to something which I'll show later. The thing is, if we would randomly select a set of images for our validation set from our data, they would be correlated with the training data, because they are basically all the same. There are lots of images here, but they are from basically the same images. So that's why we hard reserve this region for validation. Independent test data would mean we need to reserve another data set from this. That's really not working. But we do have a lower quality data set, which is kind of a different, it's also from a different broken mirror, but it's really poor quality. It's not what the beam would actually look like. It's because when they did experiments, basically that's in the wrong stage of the laser, where the laser is not as clean as it would actually be. But we use this for testing and get some interesting results. Bit of technical details. We use some K20 GPUs for training, the training parameters, and we don't do much of data augmentation here. We do have data augmentation kind of implicitly in our data set because it's noisy. We let Café randomly mirror the images, so we do get a bit field of perspective in the network. And to iterate, and training takes like 2,000 iterations. It's a small training set, so it's basically, that's fine. We will look at the loss at the very end of the talk, actually. Okay, so about performance, so that's important here because we want to do things quickly. Currently, in our proof of concept, we are not staying below the 100 millisecond mark, but I will show you why. The thing is, currently we have the filtering, feature detection done on, and the pre-processing done on CPU. We didn't go to do this on GPU yet. Inference can be easily offloaded to your GPU, so we tested this. And the filtering, that's basically FFTs back and forth to apply the bandpass filter, takes already 100 milliseconds. But all the rest, if you sum it up, takes another 100 milliseconds about. There are two things we can do about this. And the main thing would be basically just put the FFTs on GPU, and they will probably be fast enough to actually reach the goal here. And we can batch the candidate regions. This is basically assuming like a small number of, like if you are like 8 candidate regions or 7, we can stick under the 100 millisecond range. There could be, you could add another heuristics actually for this, because the number of candidate regions, if the number of candidate regions increases, we might not be able to stick below the 100 milliseconds. But if there are like 100 candidate regions in our image, there's probably something wrong anyway. So simple heuristics in this case to actually just shortcut this and just shut it down and take some time to look at it. Yeah. Okay. So now for the results. And the main part about this is the generalization ability of GoogleNet, which is, in this case, quite impressive considering what limited data we've shown it. This is a different data set. As you can see, it's really kind of noisy data, really irregular beam shapes. But we didn't use this one for training or validation. It also has a different broken mirror. It has this spot here. It has another spot here. But this spot is really well circular in this case. We didn't train it for circular shapes. We trained it for non-circular shapes, actually, which I assume would be the main sign of a broken mirror. So actually, we wanted to see this one as a true positive, and we wanted to basically ignore this one. That's basically how we defined the training set. A laser technician might say something else then in the end, because there's this problem of actually getting the data to be labeled well. So this is what the feature detection does. Basically works quite well. It gets all the like odd things in the image somehow. So we get this region, we get this edge here, we get this region, and we get some artifact over here. And if we run it through our network, we get these from these two example images I've shown before. These things as true positives. We get a list of false positives, and we get our edges, which were detected. So that works actually quite well. It's a bit surprising that this one is treated as a false positive, because based on the definition, it's actually correct, because it's kind of just a squished version of this one, but that's random that it is here. So that basically could be considered more of an error in the classification, but it's working rather well. There's something I don't give statistics in the talk because the data is so little. If I would give statistics, one picture would be 5% and doesn't tell anything. So, but it basically works, and if we had more data, basically we could improve on this and then get statistics. Counterexample, the actual training data and validation data, where this region, every feature touching this region would be was only in the validation set. So some of these features which are excluded here basically actually include this feature. Some features just show some edge here. And for example, if we classify or if we run this image, we see this type of these candidate regions. And if they're classified, we get this result. And this feature, which we reserved for the validation set, is actually classified, well, partially wrong, because that should be a true positive, because we are always classifying everything which shows a true positive and an edge as a true positive. So the network should learn this, and it learned it for this one. But apparently weren't enough examples of feature with edge to actually teach it to say, okay, if it's an edge and a feature, then it's a feature, especially. That's the important thing. So this is kind of technically correct, but it's not really what we want to have. Yeah, and here you see the main problem basically. If you have a small data set, and especially we have 3 different features here, and these 3 different features always, they look quite different from each other. So actually you want to have all 3 in your test set to actually be kind of representative of what you want to train the network for. If you reserve one of them for the validation, it is missing from the training set, and it kind of degrades the quality of our training set. We can also quantify this a bit more by looking at the loss function here. So the loss is basically, just as a reminder, how well your universal fitting function, the neural network, fits your data. And in the training data, it basically gets better and better. Basically, the moment it drops below this point, it's basically just, just increasing the softmax for the actual category it wants to classify from like 0.99 to 0.9999 or something like this. So this is not really relevant. It's good enough when it's here. Mostly because of our small data set, you don't really get these small deviations with actual wrong classifications. And the validation set, validation loss doesn't go down after this point here. And immediately it's pretty good at the beginning already, and then it doesn't really level. That does basically level off. So we would assume that it's basically not really an overfitting problem here in this case, because in overfitting you would basically see the validation loss going up sometimes. That's one thing. And we know that it does generalize to some similar problems if there's not already also an edge inside the picture with your feature. And what we see here is basically that our validation set actually contains a feature which, by its, from its shape and from its defining attributes, is not represented by our training set in this case. So there's something in the validation set which we can't learn by looking at the test set, training set. So that's a problem, big problem here. Okay, for an outlook. I told you there are different things which might go wrong in the laser. Not only mirrors can break, lenses can break too, but maybe they look different, look similar. One other thing that could happen is, I hope you can see some of this. It can be dust. There are small speckles in these pictures. They look differently in both pictures. They are basically the same dust speckles, but here it's in focus, here it's out of focus. But in both cases, it's basically what could damage the beam, basically, because dust also has this property of refracting light, focusing parts of it, or creating maxima in places where you don't want them. So this is what the feature detection makes of it, because this is a really flat, really clean beam profile, except for the dust speckles. It already reduced the threshold to 4 sigma, but it basically doesn't give you the positions of the dust speckles, which are like this. So it's not really a good relation, because these dust speckles are kind of from nature. This approach with the bandpass was designed to find these large concentric rings. These are just really small, small features. I don't know how to describe them really. in this picture. So this one doesn't work. And also, if we run it through the network, it doesn't, of course, it doesn't find these features because they look different than these things we trained it for. And then there are two things which we can hopefully do in the future when we get now more data, because since the proof of concept for this one part works, now we can hopefully get our laser operators to get us specific data to train also for this and representative data. So one thing would be like an object localization using a hierarchical sliding window approach. That's basically why in the beginning when I talked about deep learning, I said it's for learning of heuristics. Basically what we can do here, we can have three classes saying there's one feature in our window, there are multiple features in the window, or there's no feature in the window, because we actually want to find the single features. We don't want to see that there's a feature. That's the same problem, because we need to separate them so the operator can then later say this one is good, this one is bad. And in case we have multiple features, we can reiterate our algorithm and then just split up this window and do another sub-classification of this window, basically. We can here label images with bounding boxes, like it's shown here, and use this basically when we have this partitioning of the image in training. We just see, does it overlap our bounding box, and then we say, okay, this is a training example which is actually should be classified as positive or negative, or as one feature, multiple features, something like this. And the most important thing is actually get more data and also get different dust particle arrangements, because the second iteration of data we got was basically this picture. So that's a problem, but I hope now also with the proof of concept available, this will change. Here we will definitely, and we also tried some things about in this region, just defining a smaller network with a few convolution layers, a few fully connected layers for this, which can actually find these things. But I didn't try this, it works, but well, it could be overtraining because I actually only have this one image in this case, so I can't even show this result. But yeah, smaller network will improve the throughput here, and we can do lots of small image classifications. And this will basically just make this feature detection, which we made before, completely obsolete and replace it, the whole stack, basically. The other thing would be anomaly detection, which would be use some concepts of like unsupervised learning. For example, using an autoencoder, especially a convolutional autoencoder, where we pass in the image. We have some bottleneck here, which would be called the latent space also, and then we reconstruct the image. At the end, it's trained basically by reconstructing the same image perfectly. And what we would need to do is actually, we would train it with perfect images. So no features need to be in here. Then we take perfect images, pass them through, train it to basically encode perfect images. And at the end, when we pass in real data, we have features in it. And we pass in the real data image with features, but features don't fit into the latent space. So they are basically removed, or they change the image. And when we then decode it, we will have a significant difference between the encoded image and the decoded image, because the decoded image is lacking the features. And this is how we can basically basically replace the first stage only. So basically have a different way of doing the feature detection and have a second image classification stage afterwards, because this one, because then we need to basically tell the operator maybe what kind of problem this is, what we see here. Yeah, okay, sorry. To summarize, what I presented to you was the development of a safety feature for these high power lasers, so they don't damage themselves, don't create cascades, keep damage from spreading. And the special case which we looked at for now is the detection of signs of damaged mirrors in this case, and avoid spreading of this damage. If you would detect like dust things, then that's actually about avoiding damage, because dust is not damage in the system, but if we remove the dust early enough, then it doesn't cause any damage in the first place. So we basically use the physical properties of the system to do this because of the data we had available. And so this takes advantage of the smoothness of the beam, which it should have during operation. And this way we could quickly identify these candidate regions. That's something really a take-home message of this talk. I think that you put as much information that you already have that you can put into algorithms into your deep learning application, and only do the rest, which you can't code yourself. You do this with deep learning, basically. That's basically a thing. So that's also, if you think like in general machine learning, but especially also deep learning, it's like it's always generates heuristics because it is just stochastic. It's a probabilistic approach to interpreting your data and designing developing answers, basically, or giving answers. So it's only a heuristics. It doesn't develop an algorithm for it. You can't prove that it's right. So if you have an algorithm to do something, use the algorithm. And from where you don't have an algorithm, where you need heuristics and you can't get around this, there you plug in deep learning and you combine these two to basically maximum effect. The thing which kind of looks really good is the GoogleNet in this example, because it kind of could generalize to some features, even if you only had like 3 features to train it with. Which was really nice. But of course, we need more data because we still have bias in our data sets, and especially the like edge versus feature thing. We couldn't train it to do this. And of course, this problem looks like a very good candidate for anomaly detection, like using autoencoders or general adversarial networks, generative adversarial networks. And yeah, there are some problems, like the good data always contains anomalies, or at least the one we have. The operators by now told us that actually if they put some work into it, they can clean this stuff and give us perfect pictures. Yeah, so this could mean we can train an autoencoder with this. During operation, then it also is important that then features which occur, because when the laser is running for a week, features still occur in the optics, and they don't want to always clean it because that would be lots of work. So then we still go back to the thing, okay, there's a feature now, this is not bad, I just don't want to clean it, just ignore this one for now. Yeah, okay, and thank you for the attention.